In the physics of general relativity, the equivalence principle is any of several related concepts dealing with the equivalence of gravitational and inertial mass, and to Albert Einstein's observation that the gravitational force, as experienced locally while standing on a massive body, is actually the same as the pseudo-force experienced by an observer in a non-inertial frame of reference. Einstein's statement of the equality of inertial and gravitational mass. A little reflection will show that the law of the equality of the inertial and gravitational mass is equivalent to the assertion that the acceleration imparted to a body by a gravitational field is independent of the nature of the body. For Newton's equation of motion in a gravitational field, written out in full, it is only when there is numerical equality between the inertial and gravitational mass that the acceleration is independent of the nature of the body. Development of gravitation theory. Something like the equivalence principle emerged in the early 17th century, when Galileo expressed experimentally that the acceleration of a test mass due to gravitation is independent of the amount of mass being accelerated. Kepler, using Galileo's discoveries, showed knowledge of the equivalence principle by accurately describing what would occur if the Moon were stopped in its orbit and dropped towards Earth. This can be deduced without knowing if or in what manner gravity decreases with distance, but requires assuming the equivalency between gravity and inertia. If two stones were placed in any part of the world near each other, and beyond the sphere of influence of a third cognate body, these stones, like two magnetic needles, would come together in the intermediate point, each approaching the other by a space proportional to the comparative mass of the other. If the Moon and Earth were not retained in their orbits by their animal force or some other equivalent, the Earth would mount to the Moon by a 54th part of their distance, and the Moon fall towards the Earth through the other 53 parts. And they would there meet, assuming, however, that the substance of both is of the same density. Kepler, Astronomia Nova, 1609. The 1/54th ratio is Kepler's estimate of the Moon-Earth mass ratio, based on the diameters. The accuracy of his statement can be deduced by using Newton's inertia law F equals ma and Galileo's gravitational observation that distance d equals 1/2 at squared. Setting these accelerations equal for a mass is the equivalence principle. Noting the time to collision for each mass is the same gives Kepler's statement that d Moon, d'Earth equals m'Earth, m Moon. Without knowing the time to collision or how or if the acceleration force from gravity is a function of distance, Newton's gravitational theory simplified and formalized Galileo's and Kepler's ideas by recognizing Kepler's animal force or some other equivalent beyond gravity and inertia were not needed, deducing from Kepler's planetary laws how gravity reduces with distance. The equivalence principle was properly introduced by Albert Einstein in 1907, when he observed that the acceleration of bodies towards the center of the Earth at a rate of 1 gram is equivalent to the acceleration of an inertially moving body that would be observed on a rocket in free space being accelerated at a rate of 1 gram. Einstein stated it thus: "We assume the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system." Einstein, 1907. That is, being on the surface of the Earth is equivalent to being inside a spaceship that is being accelerated by its engines. The directional vector of acceleration equivalence on the surface of the Earth is up, or directly opposite the center of the planet, while the vector of acceleration in a spaceship is directly opposite from the mass ejected by its thrusters. From this principle, Einstein deduced that free fall is actually inertial motion. Objects in free fall do not experience being accelerated downward but rather weightlessness and no acceleration. In an inertial frame of reference, bodies obey Newton's first law, moving at constant velocity in straight lines. Analogously, in a curved space-time, the world line of an inertial particle or pulse of light is as straight as possible. Such a world line is called a geodesic, and from the point of view of the inertial frame is a straight line. This is why an accelerometer in free fall doesn't register any acceleration. There isn't any. As an example, an inertial body moving along a geodesic through space can be trapped into an orbit around a large gravitational mass without ever experiencing acceleration. This is possible because space is radically curved in close vicinity to a large gravitational mass. In such a situation, the geodesic lines bend inward around the center of the mass, and a free-floating inertial body will simply follow those curved geodesics into an elliptical orbit. An accelerometer on board would never record any acceleration. By contrast, in Newtonian mechanics, gravity is assumed to be a force. This force draws objects having mass towards the center of any massive body. At the Earth's surface, the force of gravity is counteracted by the mechanical resistance of the Earth's surface. So in Newtonian physics, a person at rest on the surface of a massive object is in an inertial frame of reference. These considerations suggest the following corollary to the equivalence principle, which Einstein formulated precisely in 1911. Whenever an observer detects the local presence of a force that acts on all objects in direct proportion to the inertial mass of each object, that observer is in an accelerated frame of reference. Einstein also referred to two reference frames, K and K. K is a uniform gravitational field, whereas K has no gravitational field but is uniformly accelerated such that objects in the two frames experience identical forces. We arrive at a very satisfactory interpretation of this law of experience if we assume that the systems K and K are physically exactly equivalent. That is, if we assume that we may just as well regard the system K as being in a space free from gravitational fields. If we then regard K as uniformly accelerated, this assumption of exact physical equivalence makes it impossible for us to speak of the absolute acceleration of the system of reference, just as the usual theory of relativity forbids us to talk of the absolute velocity of a system, and it makes the equal falling of all bodies in a gravitational field seem a matter of course. Einstein, 1911. This observation was the start of a process that culminated in general relativity. Einstein suggested that it should be elevated to the status of a general principle, which he called the principle of equivalence, when constructing his theory of relativity. As long as we restrict ourselves to purely mechanical processes in the realm where Newton's mechanics hold sway, we are certain of the equivalence of the systems K and K. But this view of ours will not have any deeper significance unless the systems K and K are equivalent with respect to all physical processes. That is, unless the laws of nature with respect to K are in entire agreement with those with respect to K. By assuming this to be so, we arrive at a principle which, if it is really true, has great heuristic importance. For by theoretical consideration of processes which take place relatively to a system of reference with uniform acceleration, we obtain information as to the career of processes in a homogeneous gravitational field. Einstein, 1911. Einstein combined the equivalence principle with special relativity to predict that clocks run at different rates in a gravitational potential, and light rays bend in a gravitational field, even before he developed the concept of curved spacetime. So the original equivalence principle, as described by Einstein, concluded that free fall and inertial motion were physically equivalent. This form of the equivalence principle can be stated as follows. An observer in a windowless room cannot distinguish between being on the surface of the Earth and being in a spaceship in deep space accelerating at 1 gram. This is not strictly true, because massive bodies give rise to tidal effects which are absent from an accelerating spaceship in deep space. The room, therefore, should be small enough that tidal effects can be neglected. Although the equivalence principle guided the development of general relativity, it is not a founding principle of relativity but rather a simple consequence of the geometrical nature of the theory. In general relativity, objects in free fall follow geodesics of spacetime, and what we perceive as the force of gravity is instead a result of our being unable to follow those geodesics of spacetime, because the mechanical resistance of matter prevents us from doing so. Since Einstein developed general relativity, there was a need to develop a framework to test the theory against other possible theories of gravity compatible with special relativity. This was developed by Robert Dicke as part of his program to test general relativity. Two new principles were suggested, the so-called Einstein equivalence principle and the strong equivalence principle, each of which assumes the weak equivalence principle as a starting point. They only differ in whether or not they apply to gravitational experiments. Another clarification needed is that the equivalence principle assumes a constant acceleration of 1 gram without considering the mechanics of generating 1 gram. If we do consider the mechanics of it, then we must assume the aforementioned windowless room has a fixed mass. Now, if the observer jumps inside the room, an object lying freely on the floor will decrease in weight momentarily because the acceleration is going to decrease momentarily due to the observer pushing back against the floor in order to jump. The object will then gain weight while the observer is in the air, and the resulting decreased mass of the windowless room allows greater acceleration. Lose weight again when the observer lands and pushes once more against the floor, and finally return to its initial weight afterwards. To make all these effects equal those we would measure on a planet producing 1 gram, the windowless room must be assumed to have the same mass as that planet. Additionally, the windowless room must not cause its own gravity, otherwise the scenario changes even further. These are technicalities, clearly, but practical ones if we wish the experiment to demonstrate more or less precisely the equivalence of 1 gram gravity and 1 gram acceleration.